Hi, today we're going to be talking about the Poisson distribution, and we're going to prove that the moment generating function is as given under fact 1. Then we're going to derive the mean. Okay, so here's going to be a calculus 1 fact that we need, and that is just that the Taylor series of e to the z is the summation from x being 0 to infinity of z to the x divided by x factorial. So let's prove fact 1. Okay? And the moment generating function is the expected value of e to the t times x. And that by definition is the summation from x equals 0 to infinity of e to the t times x times by p of x. Now, the probability of x is given by the Poisson distribution above, the very first formula. So we're going to write sum from x being 0 to infinity of e to the t times x, multiply by probability of x. So we'll get that. Now, the summation only involves x at this point. So e to the minus k can come outside the summation because it's just treated as a constant. So this will be e to the t times x times k to the x. We can't take k to the x out because x is in the exponent there. Now everything is being raised to the power of x in the numerator, so I'm going to rewrite that as e to the t times by k raised to the x power, all divided by x factorial. Now, this is exactly the Taylor series expansion of e to the z. If we let z equal to e to the t times k, we're going to get this. E to the minus k times e to the k times e to the t. Now we can combine exponents and we'll get e to the k, e to the t minus k, and that is equal to e to the k times e to the t minus 1. Just factoring it all out. And that is what we want to show. Now for fact 2, we should notice that the expected value of x is just this first derivative evaluated at 0. So we need to evaluate what this is. And what we'll do first is we'll take the derivative. Now this is the derivative with respect to t of e to the k times e to the t minus 1. And using the chain rule, we're going to get the derivative of the exponential is itself, the derivative of the inside function, which is the exponent, is just going to be k e to the t. Okay, so we've taken the derivative. Now I'm going to bring this back above and I'm going to evaluate it at 0. So I'm going to go, my next step is to go right here. This will be e times k, e to the 0 minus 1 times k e to the 0. Remember, e to the 0 is 1, so this will be e to the 0 times k times e to the 0, and that is just k. That is the expected value. And that's what we want to prove in item 2, that the mean of the Poisson distribution is the parameter k. Now, for proof of 3, I'm not going to prove it, I'm just going to tell you that the variance of x is this expected value of the second moment, e of x squared, minus mu squared. Now, the expected value of x squared is the second derivative evaluated at 0, and the mean we know is k, and we have to square it. So all that you have to do is calculate the second derivative of the moment generating function, evaluate it at 0, and you'll be done. Thank you very much, and that concludes our discussion of these three facts.